Which brings us to our next topic in inorganic chemistry. Transition metal, or more generally, coordination chemistry. If you take an aqueous solution of copper sulfate and slowly evaporate the water, then what you eventually get precipitating out are nice light blue crystals of copper sulfate. If you take those light blue crystals of copper sulfate and heat them moderately, the blue color will eventually disappear and you'll end up with a nice white solid instead. If you take that white solid copper sulfate and dissolve it in a 1 molar solution of sodium chloride, you get a pretty green solution. And if you add to that pretty green solution a 1 molar solution of ammonium hydroxide, you get a really dark blue solution. Which brings us to the obvious question, what's going on? The water and ammonia, of course, are colorless. The sodium sulfate and the sodium chloride would also be colorless in solution, and they're white solids as solids. So where are all these colors come from? The dark blue, the light blue, and the green? Well, apparently it has to be something that's involving the copper 2 ions. But why are they giving us all these different colors? And what difference does it make whether there's sodium chloride or ammonia in the water? Why should that make any difference? And this became one of the big questions in the 1800s. What was going on with the metals? That they were giving all these different colors depending on what else was in the solution. Why should the metals care what the other ions are doing? And so that brings us to a classic. Which brings us back to our 4 compounds. In the bottom 2, the cobalt apparently is bonded to 7 things. In the next one 8, and in the top one 9. So how can the cobalt hold on to all this other stuff? Because there isn't any question that the ammonia is only there because of the cobalt. Chloride's not doing anything to attract it. And if you have some other cation, like sodium or potassium, then the ammonias don't stay. So this is something the cobalt is doing. But what's it doing? During the 1800s, organic chemists had come up with the concept called valence. And valence was basically a question of how many bonds a given atom would want. So for example, we see in water, each of the hydrogen wants 1 bond, and the oxygen wants 2 bonds. In methane, the hydrogens each want 1 bond, and therefore the carbon would want 4 bonds. And in carbon dioxide, the carbon wants 4, the oxygens each want 2. So we need 2 oxygens for each of the carbons for everybody to be satisfied. And that seemed to work really well for organic chemistry. It was a little more difficult for the metals. For example, you could take cobalt and react it with chlorine and either get 2 chlorines or 3 chlorines attached to the cobalt. And so they were somewhat comfortable with the idea that the metals actually had a choice. They would want more than 1 valence. The cobalt could either form 3 bonds or 2 bonds. It was discovered by synthetic chemists that if he dissolved cobalt-3 chloride in an aqueous solution that included ammonia, he could in fact make 4 different compounds, depending on how he proceeded. One of the compounds, whose formula came out to be a cobalt-3 chlorides and 6 ammonias, when dissolved in water, if you added silver solution to it, would precipitate 3 equivalents of silver chloride for each equivalent of the compound you started with. The second compound, which was a cobalt-3 chlorides and only 5 ammonia molecules, only produced 2 equivalents of silver chloride when you added silver ions to it in aqueous solution. And then there was a compound of cobalt with 3 chlorides and 4 ammonias, and when you added Silver chloride got you 1 chloride. And that was purple, unless it was green. So what's going on? At this point, we have to make a short digression from the topic and go back to talking about bonding that we've already done. We are noting that if you react boron with fluorine, you get boron trifluoride. It's one of the compounds that's an exception to the octet rule, since the boron has run out of electrons before it can manage to make it to its octet. And while boron trifluoride itself is quite stable, it is nonetheless a very reactive material. For example, if you expose it to ammonia, what happens is you get a compound. The boron latches on to that pair of electrons on the ammonia and forms a covalent bond. And we end up with the compound ammonium boron trifluoride, which is in fact a nice stable compound. And the point is we have now formed a covalent bond between the nitrogen and the boron, which we've seen before. But this compound formation was somewhat different. In this case, the nitrogen and the boron did not each put in 1 electron. Rather, both the electrons came from the nitrogen. And so we call a bond formed in this fashion a coordinate covalent bond. That is where a pair of electrons are shared between 2 atoms, where just one of the atoms provides both of the electrons. And so we talk about Lewis acid-base chemistry. In a Lewis acid, the Lewis acid accepts a lone pair of electrons to form a coordinate covalent bond, whereas the base donates a lone pair of electrons to form a coordinate covalent bond. We actually see this kind of bonding in Bronsted acid-base chemistry. If you react ammonia with hydrogen chloride, the hydrogen lets go of the chlorine and latches on to the lone pair on the ammonia. We get an ammonium ion, and of course we're left with the chloride ion. And since that's obviously Bronsted acid-base chemistry, this kind of formation of a coordinate covalent bond must be also fitting into our acid-base chemistry, but now we're talking about Lewis acid-base chemistry. Which brings us to Alfred Werner. Werner came to the conclusion that the cobalt in these compounds was actually doing 2 different things. That it didn't have a single valence, that it actually had 2 valences. One he called the primary valence, which we would now refer to as the oxidation state, and a secondary valence, which we now generally consider as its coordination number. So the way Werner would divide up the cobalt 3 chloride hexammonia would be between the primary valence of the cobalt, that is, it's a +3 cation, so it would need 3 anions to balance its charge, and its secondary valence. How many things it actually wants to be holding on to? We call these things it's holding on to ligands. So the way Werner would have divided up our compounds is he used dotted lines to indicate the secondary valence bonds and solid lines for the primary valence bonds. And so he would show the 6 ammonias with dotted lines to the cobalts and the 3 chlorides with solid lines to the cobalt. In modern nomenclature, we have a square bracket and the cobalt along with the 6 ammonias which are bonded directly to it inside a square brackets, and the chlorides which are not directly bonded to the cobalt outside. For our second compound, which had 5 ammonias and 3 chlorides, there are only 5 ammonias, so we are short 1 spot in the inner sphere for the cobalt. And so one of the chlorides has to do double duty. It's both primary valence and secondary valence, and so it goes inside our square brackets as one of the 6 ligands that are actually directly attached to the cobalt. For the last 2 compounds, with the 4 ammonias and 3 chlorides, With only 4 ammonias, we need 2 of the chlorides to be inner shell ligands, and only 1 of them to be outer sphere. And so we see the consequences when we dissolve the compounds into a solution. The top cobalt with the 6 ammonias dissolves as a single piece, that's a whole complex. And the 3 chlorides are simply available in solution since they're not actually directly bonded to the cobalt. For the second one, only 2 of the chlorides are available around in the solution because the one that's in the inner sphere is actually stuck to the cobalt. And finally, in our last case, 2 of the chlorides are directly stuck to the cobalt, and therefore in solution that one only has 1 available to be precipitated by the silver nitrate. We don't use Werner's notation anymore in talking about metal complexes. Instead, we separate the metal complexes by putting them in square brackets. Within the square brackets, you first list the metal center, whatever metal is at the center of the complex. You then list the ligands that are directly bonded to it, that is, its inner sphere ligands, and you list them in alphabetical order if you have different ones available. And finally, outside the brackets, you would put any extra ions that have to be associated with the complex. We've already looked at how, through the modern way of writing the cobalt ammonium chloride, as an example, where the metal complex is in fact an anion rather than the cation part of the formula, we have potassium platinum 2 chloride. And in this case, potassium goes outside. Inside the brackets are the platinum and its 4 ligands, the chlorides. And that brings us to the end of today's discussion of coordination chemistry. See you next time.